Hi everyone, this is another video. I am going to recap of the lecture that I delivered last evening. And I try to use that interactive way to show you how we can understand the PE format. Currently, you see a slide which shows the basic structure of the PE file. So based on the color, you can see DOS header. After the DOS header, there should be some gap area right here. We call the DOS stub, and then we can see the PE signature. The DOS stub, um, I don't know why. Sometimes some binary may have some more space, so that the design from the DOS header at the end of these D-word character, two D-word, is a pointer pointing to the next section of the PE header. And after that, you can see the P header or cove header or anti header, whatever you want to name it. And then we will be able to find the optional header. And after the optional header, we may be able to see different tables or maybe a data directory. So that is the basic of the PE format. Actually, PE is a file. This file is a binary format. It followed the Microsoft Cove or PE documentation, which I can remember around 80 pages or 78 pages. Those materials are quite dry, but it explains how these PE format need to be structured so that the window loader can load the image according to the specification defined by the header or the metadata of the structure to map it into the virtual memory when a user try to run a program by double-click the icon. So a couple of things we need to understand before we dive deep in the PE format. The first thing is PE file is have some kind of boundary of each chunk of data need to be mapped to the virtual machine, to the virtual memory. And actually, each chunk of data, they do have some defined size, just like a container, ship container. Each content, which is the data in PE file, need to be accommodated inside a standardized unit. We call the file alignment, which is in the PE file. File alignment in PE, most of the design is 512 byte, which is translate into Hesse decimal should be 200. So for example, if the DOS header, for example, here, if the DOS header, the size is more than 512 byte, 512 byte. For example, if that the DOS header plus the DOS stub, these two items, more than, for example, 512 byte or 200, if the size is the actual data contained inside these two sections of data have 30 byte, for example. Then in the design of the PE alignment, it may require 400 to hold this 300 data. That is 100 space is marked as 000, which is waste. So this is the concept of the file alignment. But in the case in the window loader, load this chunk of data into the memory. In the virtual memory, basically the virtual memory alignment size is 100, which is equal to 4096 bytes, which is we usually call it 4K data chunk. So that is case if we have the DOS header 300 mapped to the um, virtual memory, then it may have 700 or maybe more than that actually, because this is hexadecimal. A lot of empty space are wasted in that way. By arranging that, may have more flexibility, more easy to manage by the program, by that kind of thing. But that create of difficulty for human to always our human mind. First, we are not binary system. Hexadecimal difficult to change. We use the decimal system, and then we always mix up the alignment thing. So let us try to go through another slide that shows everything about the PE format. Basically, after the PE header, then we may be able to see the immediate following the PE header. We may have the section table is showing something in this when we talk about the when we moving the BinText as an example of this video demo. We put it in the PE Bear, one of the PE tools, so you can see the section table right here. Later on, I will show you the demo in the VM, so you may have a better understanding after showing you this part. And then you will be able to find different sections. One section is called text section, which is the executable code section. And then another section, for example, .data section, which usually holds the global or static variable. Resources section may host the menu, bitmap, dialog, string, icon, blah, blah, blah. And then some more other section. So one thing I need to emphasize, and each section table, we have different data information. At the end, there is a piece of information called characteristic, which is responsible to tell the window loader this section when it was mapped to the virtual memory. The virtual memory permission will be live in that area. A typical example for the dot text, which is the code section, usually marked as R and X, meaning read and executable, not writable. For the other location, may have read, write, you can read it or write it, but cannot be executable. So that is the way we have a brief idea what is the PE before we go into the VM to check everything. In this video, I try to using different kind of PE tool. Here are, for example, on left-hand side is the PE Studio. Usually we use this for analyzing malware, but when we study the PE format, we may use some other tools. Of course, in a Linux environment, we can run the op dump, object dump by different command. So you can try put the sample or any Windows binary inside Linux and then try to use the object dump function to see the PE structure. But remind you, the most of the tool in the virtual machine that is Windows 10 environment and GUI interface is easier for the early for the new learner on understanding the PE format. In our example, we heavily use PE stood PE to understand it. This diagram shows another way to present the PE structure. The drawings is quite good. It's just like some kind of three-dimensional way. It simplifies the one of the binary with header and section. In the header, we may have the DOS header, PE header, optional header, embedded inside the PE header, and then we have data directory, which is I think there should be 16 of that. We only concern two of that this video. One is the export. Usually export is not related with EXE, but related with the DLL because it provide an option for other binary to call into a particular function offered by that DLL library. And then another section is the import table or import directory. This import directory will provide the information. I think that it should be 2D word, uh, and then one shows the size of the the size of the function that will be used by that particular binary. And another part is showing the location of the which library, which DLL will be used, and then each function will be able to identify in a entry record. There's no entry record terminology in the PE documentation. I just created for you to have some idea. Basic unit is 20 byte, not 20, it's 20, because there is five block of data. Only three of them are available for us to find out the pointer location, to find out the exact symbol name or function name, and the library name, that is the DLL name. We can find out by the pointer contained inside the import address table lies in the section right here. So let us right now go to the virtual machine. Okay, this is new returned to the initial snapshot as usual. So everything is clean right here. So let us first find out the location of the BinText because we use BinText and as an example. The first PE tool we can use is the built into file analyzer. So you right click it and go to the file analyzer. So you will see the hash information and the version information, size of the binary. That is not our concern. First thing we need to see is NZ header. So NZ may contain a signature or magic content or magic indicator we call the A5A4D. This is important. 5A4D is the SD character or MZ. Okay, so it contains different information. Basically, the first 2 bytes of each PE file is 5A4D. So if you see the 5A4D in the memory, that means that is a high chance that is beginning of a PE file or PE format in the virtual memory. Another part is the PE header. Okay, the PE header also bears a signature. Here you see a D word character with 4550. It shows a little bit rare, 4550 and translate in the PE, the P supposed to be 50 instead of 45. We need to do some little Indian change on this particular information. And also you will be able to find a few inside this section that marked it as 014C. This 014C will be provided in a table of the Microsoft PE documentation indicating that this is matching to the Intel 386. Another field you may want to have a look. Any local time means the time changing from the UTC, but information contained inside the PE file is represented in the UTC time zone. So it was compiled in 2009, April 15 UTC time, but converted from this strings, this content right here. And you can also find some more information, for example, the file alignment. I saw the file alignment somewhere. Should be, yeah. You see the file alignment is 200. Section alignments referring to each section in the virtual memory is 100. So this is 512 byte, 512 byte. This is 4096 byte. So the oldest version is 004, which represent the Windows NT and forward. You don't see Windows 10, Windows 8, Windows 10, Windows whatever, because after the design published the document, any after NT, everything is referring to the 4. So in the PE section, that is the section that I referred to. You remember the last slide that I present. Maybe I can swap to that page so that you can have a better look on the slide and then come back to the virtual machine later. Okay, the section exactly is the location right here. When we use the virtual machine, especially we put the BinText inside the StudPD, we can study. We have a tool to show the section and exact location of the data lies in the headers part. However, the StudPV will not show you the interactively show you the location of the section. Don't worry, but basically, if we have any text editor, we can find it out more easily, which is the section just immediately below the header. The only thing we change is the door setter. When we talk about the end of the door setter, we have a pointer to the PE header. And this gap in between is variable for each compiled binary. But the section just immediate after the header, that is the design. So we now go back to our virtual machine to see the section table or sections section table of the BinText. Okay, now we go back to the file analyzer to check the PE section. Text means the code section. So you will see the text section have some number right here. This 3432 is hexadecimal, 3432 byte need to be used inside the virtual memory. So it is the meaning of virtual size. So it lies on the offset of 1000. What else in between offset 0 to 0 FFFF? So this is not showing right here, but basically they are the header. Okay, all kind of headers, including the section table, and then it will end with the size of FFF. FFF plus 1 is 1000. So anything in between that should be in the, or we call simply call the headers and section. So the virtual size will be starting from offset 1000. And the physical size means the raw size is 3600. So in the raw size, or that is referring to the PE file on the file. So the file offsets from 0 to 3600. It can contain the size of 3432. Okay, so each alignment in physical size is 200. Each alignment in the virtual size is 100. So you see any increment from each section to hold different size of data in virtual environment should be in the unit of 100. So 100 minus 500 minus 100, that means in between this section, that means the text section should have 4000 in the defined area inside the virtual memory of a particular process. And the data can healthily save inside this 400. 500 minus 100, we have 400, and 3432 can accommodate that. Also, 3432 can easily accommodate inside the physical size, which is 3600. Okay, the next chunk of data should be 3800 because its increment size is a basic unit of file alignment 200. The physical address is start from 400. Why start from 400? Because the DOS header and the section information more than one chunk of data. It needs two chunks of data to hold it. So that two chunks of data, two block of data, each unit is file alignment 200 add up for the end of the code section should be lies in VFF, which is after adding 1 byte change to 400. So it's quite clear. Also, we do have a flag. Some other tool may call it is characteristic. It shows basically the flag is very important because it controls the read, write, and execute permission. Later on, we can use another tool called PE-bear. I can show you the same binary inside will have what kind of permission shown to you. So our data section is something like that. Also, the assuming in the virtual size in the virtual, when that section when load or mapped by the window loader to the virtual memory, we will store up, it will at least using 1D6A. So 1D6A are good to save in 200. The 200 is the 700 minus 500. So we have 200 in the virtual address can easily accommodate 1D6A. And what about the raw? What about the physical? What about the file? The files should be have 1E00, easily can accommodate 1DEA. You understand it? Okay, so how to calculate the size? 5x00 minus 3a00, then you have the 1e00. And the fact is for whatever, which may be uh, the last one, previous one, 6, whatever, 0, 2, 0, may be the read represent the read and executable. This is some other features, maybe read, write, execute, or whatever kind of combination. But usually this is not executable. And data section in the virtual side, if the program running in the virtual environment, it requires four D10 size, D10 space to hold the data, uh, and then and then 8 minus 7, we have 100 of that means 4K data space in the virtual memory, easily can hold D10. However, in the physical size, the trunk is only using the minimum section, minimum space, minimum block of 200. So how come 200 can hold D10? This is a some kind of idea that I cannot make it clear in a couple of years ago. And how this happened, I can tell you right now because when I check with the data inside the physical size of BinText, actually I don't find D10 size. I can find 34, 32, I can find 1D6A in the physical size of the data structure, but I cannot find any material data in the size of D10, because if I measure this, it will jump over to the another section, and that is a lot of the size actually in the physical size is not that large. Maybe this is one of the reason caused by the if the binary running inside the virtual memory, those global variables will be expanded. It requires more data space to hold the when the program is running. So the same thing, the different features permission will be governed by this set of data, and then resources section is like that. So that is the most important part I want to show you about the PE file. Another part, I want to explain it later, but I can show you right here first. The first is you can see it is the import IAT import address table based on the IAT to find the import function name. The first function is COMCTL32DLL. Inside this DL4 function will be used by BinText. And the first function is called image list at mask. So see if we can show you in the same video how I can use human mind to calculate the pointer mapping from the changing from the raw to RVA. RVA means relative virtual address, and then change the data into interpret the data in by way of little endian, and then we can identify what is the raw location of these information, such as the function name, COMCTL32, and I mean the library name, COMCTL32, and the function name, first function name of image list at mask. So export, you don't see anything for the BinText. So let us show this inside the PE bear. So PE do have a different way to present the PE information. For example, it specially highlight to you the entry point is 362D. This is RVA. Okay, so we click to the location of DOS header. We see the same 5A40 things right here. and file header, you will see the some other information for 14C. Here we have some other whatever which header. This is another way to present only by the PE viewer. Now we go to the section. I said the section is important because it shows you the information that we previously go over. In typical example, here we see the virtual size require D10 to allow the BinText can running smoothly. However, in raw size, the space to hold the data is far less than D10. Actually, when I using another tool to find it out, it is we don't have that piece of information. By the way, I want to jump into install a program that has been provided inside the VM, but you need to install it. I used this program to show you we don't have to zero data indeed in the file or in the PE raw data. But when we running, maybe more information is inside here. So let us install the program now. The program is called File Insight. We go to Support Tool, File Insight, just double click it. If you don't want to see how the program installed, just skip this part. So I go to the File Insight. Now open the BinText in the tools basic. Yeah. Now you see the P format in different environment. This file insight, we can actually modify the code in the HESI editor and then save back to the file that I can modify things right here. In a section, you will see the text section start of 400. Yes, the same as I show you when we are using the tool called file analyzer. Section. Can I have the section information? Yeah, you see, it starts from source 00. So actually, the data, this is a text editor that is raw or that is PE, that is image, start from here. Anything about that is unused. We have the DOS header. We don't have exact size, but I know that the DOS header usually lies in 3FF location. Okay, 3FF location. And then after that, that is the door stop, and then the pointer is F8. So we go to F8. That is the this D word representing the PE signature. We can see this. And also the most important part is the input. So I will use this later on to show you the input of the stuff. So if we measure from the raw size or PE, if we count it from at the location 1E00, at the end, if we calculate, should be the raw size at the location of 5X00. We count 20 bytes to see do we have the data size of D10 or less than 200 inside the file insight. So file insight will go to the absolute address offset of 5X00. Now, how can I go there? Of course, one way is scroll down, another way I can do a search. Go to I go to the absolute address offset 5800, or maybe I need to type 05800, see if I'm correct. Yeah, I'm correct. So if we measure 2008, that means measure 200 was the size in hexadecimal should be A00, right? So let me check, are there any meaningful data starting from 5x00 on the raw? Do we have more than 200 or even the size of D10? So I move to 5800. You see a lot of empty space right here. And actually, the size of the data right here is 200. If the actual data has meaningful data, if I counted 01 is meaningful, and I'm moving back to the 5x00, which is a beginning offset of this chunk of data, we only have the size 131, less than 20. However, if I run this in the memory, if I run the BinText in the memory, the size is much larger. Let's see if I can run the BinText. Uh, Let me turn on the process hacker. Maybe I can find out what is the size right there. The process hacker to have better feature to check the memory and handles when compared with the process explorer. So I have this. Let me run the P file called the BinText. And if I double click the BinText, you will be displayed with the size of the, the memory location in the virtual memory of the BinText. Now, see if I can find the BinText right here. The PE file. Yes, it's that at 400. Here we got the same information um, similar to the raw file, starting with the 45A. However, I want to check if this raw file mapped to the memory. I need to find the, because the file alignment is different. This is measured by 200, this measured by 1000. Then I check using the table. The table of the information telling me that if I move to the 700, I suppose be able to find the size of D10 instead of 200. I may have more data than the actual data lies in the raw size is 131. Why 131? Because I checked this one, everything is empty. That is 131 in actual size in this section. This data section maybe contain the global variable or static variable, something like that. So if we come over to this, we move to 700, see if I can do the search, go to this file offset, see if I can type 700. Yeah, too large. So I just drag it to 700. Can I do that? Oh, it exceeds this part. So I need to find some other location. It must be aligned in some other way. Maybe here. So this chunk of data, third chunk of data, this is the first, second, third, yeah, is measured from 500 to 700. So let me check the 700, the first chunk of data, how many data right here in the memory. So this is the beginning, and see if I can do some comparison right here at the top of this section. We start with 40CA43, not this section. Then see if I can find the other part or maybe this part, not this part, not this part. Exit, this is not the BinText, this is local. Um, I once be able to find the things in the memory, but it is not successful. 3FF0, and this size is 3800. I suppose correct. I suppose be able to identify it right here, isn't it? The size is 3FF. This size is 1FF. This size is FF5. It seems the size is like that. If I find this, see if I can find the same thing in here. CA43. It's hard to locate it, but sorry, I cannot find it right now. Maybe you can try at home. So it explained in the raw, this demo show you something that we need to be aware. Uh, the demo shows the raw size 200 is sufficiently holds the data information of 131. However, this 131 data, when it moved to the virtual environment, it requires the space much larger than that we need the D10. That's still okay because D10 will safely be able to hold inside the data between 7 to 8, which is 1004K. And the data of 131 could be able to store as this 200. So we spent too much time on this part. Now let us try to using the tool called step PE so that we can understand the structure more in a way that we are supposed to do. So we use a tool called step PE, which I put it on the desktop and put the BinText there on. I want to use this because it's more easy to understand the error message because I'm running the PE file. It's handled on that it aware with. So you can find the same information. For example, the entry point is 422D. If I turn on this tool using file analyzer, um, here, 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 file analyzer. Yes, please come out. Oh, it's already here. If I turn on this and go to the PE header and set header, see if I can find the entry point here. Where's the entry point? 422D. We have 422D entry point. But bear in mind, highlight in red, it is RVA, relative virtual address. That is the entry point in the virtual memory. The entry point in the raw lies in 362D. What does it mean? Go back to the file analyzer, see if I can find that 362D and show you. File analyzer, open the BinText. I need to go to the location of entry point that's 362D, then search absolute 362D, and I find CB, and I find 55XB easy. If I go to disassemble, we find push EBP, and then move stack pointer to the base pointer. So this is the information lies in the entry point but the entry point lies in the raw at the offset of V62F. However, when we are in the memory, it's different. Uh, See if I can show you by other things. No, until I can find it in the disassembler or debugger. See if I can shut down the BinText, but using the debugger to hold the section. It will be more easy for me to show you about the BinText in the memory. Yeah, we always need to move in the same binary inside the memory and compare the data contained inside the image. So we drag it to the Win debugger, and then now in the debugger. By the way, in this demo, we'll show you how to use the tool such X32DBG and IDAPO. So in the first time, I assume the first time you never touch with the debugger. I give a very brief introduction right here. I have no time to teach you how to use the tool. You need to learn by your own self. Here is the CPU pane. Here's the register, CPU register location. EAX usually hold back any call lab program to call the call E program, and the call E program will process the data or process the information submitted by the call function, and then the result usually put back in the EAX register. And anything, if I run this instruction one step and we go to, we'll make some change of the instruction pointer, always pointing to next location. For example, this is 77CEE9C7, that is location. If I hit run, jump over or step over one step, it will go to this location. But I'm not going to do that at this moment. This part is the stack. You will see the stack will always increase by using the design for subtract, because the stack is going from top to the to higher memory to the lower memory. Is the dumb area. This spaces sometimes provide meaningful information for us to monitor. We need to aware where are we right now. We usually X32 DBG or X64 DBG will put you inside the region of ntdll.dll. If you want to do a search the string right here, you only show the string contained inside the ntdll.dll. It is not the BinText. So the first thing we would need to do either plus this the run to the stop at the entry point, or we can go to the user code. So let me try to type the go to the run. It stop the entry point. You see the entry point is 422D. The instruction code is 5588EC. That translate into instruction code, or some people call it assembly code, but not exactly. That is CPU instruction code, pushing the EBP, that is EBP data to the stack. And then the stack pointer, moving stack pointer to DBT, stack pointer is right here, move this one line FF74 to here. That is the thing. My purpose to showing the BinText in the debugger is trying to tell you that the entry point in the virtual memory is 422D. However, the step P tells us the entry point location in raw lies in offset file offset of 362D, and file analyzer prove it to you. It lies in this location, 362D. 362D contain the assembly code of 558BEC, same as the information in the Yeah, let's debugger 55XBEC. So that is always have something we need to bear in mind when we analyze, when we try to dive deep in the PE file because of file alignment and because of the data contained the Lithuanian and because of the data show inside the address only show the RVA instead of the VA, then you may have different picture. If we put back the BinText in the PE bear, and if we click the section header, you will see the red line. The red line in raw tells you the entry point at 362D. However, in virtual, just like the debugger, it lies in 422D. So this explain you by using different kind of tool that all the concept you need to understand about PE may have some difficulty for human mind. You need to change your mindset into a machine way to understand the data exactly. But StepPE only give you an interactive way to allow you to dive deep in PE. I hope you understand why I do this again in the video. So let us move to another part. We want to check each section, each header, and the pointer relationship in more in-depth. Let me turn on the zoom. It's already there. No, I just need to make this function, the tools working so that I can enlarge. See if I can enlarge. No, let me do it again. Okay, already in use in different Zoom. Okay, so how about we close down this one and then we can keep this in the memory so that we can check the memory instead of using the processor. Then we try to use read only. Don't worry, it's just read only because a handle was created in between right here. Yeah, this is some kind of handle right here. Now, first part, if we click this button, basic header, okay, can I do it again? Control 2, see if I can change it. Control 2, it doesn't work. Forget it. So here you will see that the size of the DOS header, if we click the DOS header, it is 3F. Okay, then or maybe let me shut down everything and try try to use the so see it is working. Now it's supposed to work. Yeah. So I enlarged this because I want to show you the DOS header. At the end of DOS header, there's a pointer point to the next section called the code header. Okay. Yeah. The starting location offset, this is raw, this is image. The raw size, the first 2 bytes is 45A. And the end of the DOS header at the location of 30 or 389 A, B, C, D, and then you will find F8. This F8 is presented in Lithuanian so that if we want to find the pointer point to the location, so it lies on the address of offset address of F8. So F8 is here. So this is the pointer is pointing to the location of the next section data. Each binary may have different pointer, so that the content right here will be different. But after that, every section we just finish the section, and then another section will immediately follow another byte. There's no more pointer for the sections and header. But there we have some information contained, for example, in import address table, that is a pointer will point to the actual data of the library name, for example, kernel 42 DLL, and the function name. That is another issue. But when we using the step P to analyze it, this is the only pointer we need to be aware of. Then if we want to find the magic number right here, we can find a pointer right here. It's very clear. You can do it at home. And the second chunk of data is the code file header or NT file header or PE file header. And this word so this keyword show you the PE file. No need to convert as Lithuanian. And then the other, for example, 4C01, you remember that is representing, according to Microsoft PE documentation, this code referring to I386 machine. So we have the signature machine. We have the number of section. How many section right here? We have 4. This is Lithuanian. Timestamp. Okay, now we need to check the timestamp. Timestamp at the address of offset of 10 on the image. It shows the x6, 46, x6, 46, e6, 49. However, this is need to be converted to Lithuanian before we do the time conversion from code to the human understanding time. So let us go back to the file. I'm using file analyzer, right click and select the file analyzer. Then we go to the P header. You need to check the data. This data, when compared with this set of data, is the real meaning of the changing from the PE section, changing from machine understandable, CPU understandable, Lithuanian to human understandable data information. Now see if I can show on the same screen. Okay, this X6 46 E6 49 is Lithuanian way to present the data in a raw file. The order should we need to cut it into middle and change it 49 change to E6 and then X6 change to 46 and then this chunk of data moved in the front. So we come to the 49 E6 mapping with this. Is it okay for you? The other I don't mark, maybe I can mark the line on the top. 4686 we change that is coming from this chunk of data. This is from here. So you see this how to do the Lithuanian conversion. Okay, so no more discussion. And if you want to see this, whether it is good or bad, you can try to using the Win debugger. I just show you once. Usually I don't show it, but this is video. I do have time to do it. Convert the format, what's the information contained right here. See if I can copy the value to some location. Let me turn on the lookback. Well, this is always annoying. Can I shut it down? Yes, I can do it. No, sorry. It doesn't matter. Don't spend too much time on it. Then if we want to do this and do a copy to the Win debugger, format space, they convert the timestamp to you just like the uh, PE, just like the file analyzer at the same time. So that we need to convert to supply the data, uh, convert from the raw by using Lithuanian way into the data, and then data need to be converted into the format of time. Well, really complicated, right? Yes, I have to say that to understand it, that is the best way is interactive to analyze the data by item. I always pick up myself, but sometimes you need to be aware that if you want to dive deep in the PE, you need to use the way to your methodology, your approach to understand it. Reading the Microsoft PE documentation is definitely a formal way, but it's really, really hard to understand without example. Here, interactive example by using step PE helps you a lot. Now, we go to the characteristic of the PE file or the image. So here we call the characteristic. What does it mean? This is 2 by 16 bit, and each bit will allow you, if they are turned on, that will turn to that will be showing into one, and then if it's not turned on without the check mark, it's a zero. And only one thing I want to mention in this class, if you find the file P file, if that is .exe, it doesn't necessarily that is executable. And if you find a file with .dll, it doesn't mean that it is must be a library of DLL, dynamic load library, because Windows Loader doesn't care. It doesn't care anything. It just care about whether this bit is turned on or not turned on. So finish this part, then we go to the optional header. Optional header, the size. What is the size? It starts from the offset 110. The size is like this. It's 60. 60, if I need to convert it to be supposedly 96 byte, I think. So this 96 byte contain the optional header. After that, suppose we have the data directory. The data directory supposed to start at 170. To confirm it, just click it right here, 170. This section we call the directory, data directory, contain the export table, import table, which we refer import table, we have the pointer and the size of the entry. And what is the size of this trunk? The data directory size is with the size of 8F. I think 2 something, maybe I can't remember. You can do using the calculator to do the can I just shut it down? Sorry. Yeah, what are this? Then if I using a calculator, we change it into the programmer calculator, the size 8F, then I go to hexi, 8F, change to deci, is 143. The size is 143. Am I correct? Oh, this is only referring to the data directory. Okay, so that is X0, not that size. X0 converted into decimal is 128 byte. So 128 byte, if I go back to my standard calculator, 128 divided by 16, oops, sorry. 128 divided by 16. Each of them have 8 byte. That is each table size. So after this directory table, step PE will not show you any furthermore. But actually, if we extend it, you can see something. If we find anything away from this part. If we check this, you will be able to find out some meaningful data. The size is 28. The calculator is not 28, 28. We change it to hexadecimal 28 goes to the decimal is 40 byte. 40 byte of each data trunk after the data directory is that shows the information to you. That is the section. You see the text right here, SD character, and then you find some other things. See if I can click into here. Yeah, it shows it right here. This is text section. You see this is the text, and then you see 34332, the virtual size. This is Lithuanian right here. So I let you do it and check it by your own self. But now we go back to the optional header, see if we can have anything we need to aware with. The magic character right here. And then we can check the entry point for 2D, for 2D. Actually, this is RVA, not VA, I showed you before. The image base is 400, but it shows in the so we do need to an Indian way to check for the section alignment. That is alignment in the virtual memory. File alignment. That's alignment in Lithuanian in the raw data. That means the PE file. So some other things. I let you to study the content. Let me stop here and go back to the slide, and I go over a little bit information about the import adjust table. Import adjust state table is lies in this location, and its size is the size of these is 8 byte. We divide it into two parts. This part is the size. This part is the pointer. It points to RVA. RVA, sorry. RVA. And we need to do the Lithuanian should be 625C. Remember that. So we go to the slide. Now we go to the slide. The slide will show you exactly thing. Our starting point is the in the data directory of the image, the import table pointer. That is 8 byte data that I copied right here. And separate into two chunks of data, do the Lithuanian in that part A00000 change to A0. That representing the size, how many bytes of data will contain in the import address table. And then now we can see that do the RVA change to 625C. And 65C, we need to do some calculation. I think you can still remember when we go to the section of text section, and you find the section table, virtual size is starting from 500, and then in the raw is 3800. So we need to change the 625C from RVA to raw. That is the way to do the calculation. But all the tool will do it automatically to you. If you want to understand, you need to do the calculation just like what I'm doing right here. In the 625C, this piece of information is RVA, and then we need to change to the raw. The raw offset is 4C5C. And from 4C5C, we count 20 bytes. This 20 byte can divide it into 5 chunks of data. This FC62 will move into here, and then two empty 8 byte, and then we have 007265, and then blah 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 50. By doing this kind of thing, we do some kind of different conversion. For example, 7265 RVA change into RVA should be 6572. 6572 change to raw is 4F72. If I go to the offset 4F72 in the file analyzer of the BinText, I may be able to find this. Similar, this 50 change in that is RVA, change it into the Lithuanian, and then we change to that pointer we're pointing to raw, that is 3A, and then 3A will point to another ton of data. We need to do one more conversion to find the image list create. So the calculation is complicated. I try to show you this demonstration. You go back to virtual machine. That is the best effort I can explain what the RVA and VA arrangement. Okay, I'll go back to our screen about the step PD right here. And the table, you can see previously, this is the size, not my concern. 625C, we change to 5C62, need to Indian change to 625C, but we need to calculate the raw address. So inside the std PE, if the binary have been null by std PE, we have a way to do it more easily. That is a button called RVA to raw. We don't need to calculate each of them. The relative virtual address RVA, what is the RVA? That is right here. RVA 625C, right? 625C. So let me type 625C. It automatically convert to us 4C5C. So what is 4C5C? I want to take out the actual data in the binary in 4C5C. If the std PE is good enough, I suppose you can be able to locate the raw data in the 4C5C address. However, the limitation of std PE, I need to use another tool, that is the file inside. I need to load the BinText. I need to go to the exact location of 4C5C. So I'll go to search and then go to absolute location 0x4C5C. So I find the information is FC62 blah blah blah, and then up to 50. 20 by 1812 means 20, isn't it? Yeah, 16 plus 2, 16 plus 4. I think this one up to here. Okay, so if you refer back, or maybe up to right here, I'm not quite sure. Anyway, we need to have 16. That is 16, 17, 18, 19, 20. Yeah, the size should be like this. This chunk of data, I need to find, for example, I need 7265 to location. That's RVA. We need to find 6572. That is the location pointed to identify the library name, first library name. Well, what is the first library? If we go to file analyzer right here, go back. Yeah, I told you many tools. We need to changing these different tools to to allow us to analyze the PE in depth. Here you see the first function is called CTL32DLL. Then we go back to our step PD. I have the information of 6572 as RVA. Yeah, move down a little bit. RVA, if that is information of 6572, the raw is 4F72. 4F72, sorry, I need to go to the exact location of 4F72. So go 4F72. I find 4F43, isn't it? Sorry. Actually, I already found the library name. That started this location. That is the library name. Aligned with the file analyzer interpreted result. So how about I do one more thing, try to find the function. The first function in the file analyzer is the image list at mask. How to find it? So we need to go back. We need to go back to the address. The address of the RVA should be, I mean, the first chunk of 20 byte data should be 00500. So let me try to go to the exact location of 5000. Is it the pointer? Give me a second. Let me stop recording. I need to find out from the slide. Okay, go back to the slide. It is more clear. I need to find the RVA at the address of 50 should point to the raw of 3A. Then from 3A00 in raw, RVA is 500, raw is 3A. So I go back to my virtual machine, then I show you the remaining part. Okay, let me go back to step PE RVA correction to raw. 500 here. I need to find 3A00. So in the raw file under the file inside, I go to the relative address 3A00. Okay, I got 3065. 3065, that is RVA. I need to change it to 6530. Then where's the raw location? The raw location of 6530, it lies in 4F30 in raw. 4F30. Then I go to 4F30. You will be rewarded if you do have patience. That is the gospel of deep dive in PG format. So that is the maximum thing I can do. I try to create a Word document and try to map everything manually by using tool or something I showed you previously, but I won't do it again. I hope this video can explain all 10 years difficulty in understanding of deep dive of PE. I hope any future instructor or some other people can have a better way to explain this difficult concept, deep dive in PE, to the future user. Okay, that ends for this demonstration.